We're now going to construct a generalized equation for conservation of energy that will be our go-to equation anytime we want to use energy to problem solve a problem. We're unsure where to start. We will start with the general equation we're about to construct. And we construct it through, as it says here, the Chapter 7 work kinetic energy theorem, where we're taking the net work, and as we have shown before, we're breaking it into two categories of conservative and non-conservative. Our conservative work is done by springs and gravity for us in this course, and the non-conservative force will be the frictional force and or applied forces, which will always do work over any delta x that they cover. So it's not just the endpoints like it is for springs and gravity. Well, let's see how this works out. All we are doing here, quite simply, is plugging in negative delta U for work conservative. So we go from our work kinetic energy theorem very quickly to negative delta U plus work non-conservative equals delta K. We just rearrange the equation, and there you have it. This is our generalized equation. Now we're going to use a slightly different form for it, so we'll get to that in 2 seconds. But first we can see that if we take the delta out and look at just kinetic plus potential, K plus U, that is, by definition, 3 equal signs, right? The total mechanical energy. And that should make sense, that it's the total energy, mechanical, because we're not looking at electrical or chemical energy. It's mechanical energy, it's motion energy. That if we know the kinetic energy of the object in joules, and we know the potential energy available to it in joules, when we add those two joule values together, we will get the total available energy at any instant in time, and that is called the total mechanical energy. ME, sometimes just E. Here we go, though, with our go-to equation that we are going to use to problem solve any energy question. When we are unsure where to start, we will start with this equation. So it is saying that the work done by non-conservative forces, which for us will always be friction, if friction is in the problem. Friction will always be negative work, meaning friction is taking energy away. All of the delta x matters, right? So delta x up, back, sideways, it doesn't matter. If it's moving, friction is taking energy out. Now, the work done by applied forces will not always appear in problems, but if it does, and the force is working with the object, speeding it up, that applied force dot delta x will be positive. If the force, like friction, the applied force is pulling backwards on the object, slowing it down, then we would have a negative. So work done by friction plus work done by applied equals kinetic plus potential final minus kinetic plus potential initial. And now the potential energy can have both the spring and gravity if it's a vertical spring problem, where the spring compression is the x, and the vertical motion would also give us an mgy to look at. So please write this down. I did not put this into the notes because I wanted you to get used to writing it, because this is the equation you are going to have to write down to problem solve problems using energy, conservation of energy, most especially if you're unsure where to start. Now, we're going to look at a very special case of problems where there are no non-conservative forces. So if there is no friction in the problem, if there's no friction, you don't put friction in. So if there's no friction, and if they don't give you any applied forces, so basically the only forces in the problem are springs and gravity, then what happens? Well, that's our next page of notes. What happens is you lose the whole left side of the equal sign. So when friction and applied forces are 0 or negligible, and it can't be iffy, you have to explicitly be told within the question whether they are 0 or negligible, the left-hand side then goes to 0. We have kinetic plus potential final minus kinetic plus potential initial equals 0. And if we rearrange that, we get kinetic plus potential initial has to equal kinetic plus potential final. Conservation of energy, whatever was ever there initially, has to be there finally. No friction, no energy losses. So as soon as you see, as it says here, as soon as you see there's no friction, no applied forces, we will go directly to this equation. We will use this to solve many problems. Kinetic plus potential equals kinetic plus potential. So there we have our basic structure to problem solve our energy conservation problems with. We will use this equation with no friction, and we will use this equation with friction, and if we have to add an applied force, we do. So please make sure you have your notes annotated properly, and hopefully problem solving will be much better now for you.